right, hey everybody. So this week, which is we're closing in on the end of the year. The last subject that we're going to talk about, which is related to the last couple of weeks in terms of temperature and motion of particles and molecules, is a series of topics called the gas laws, and it talks about the behavior of substances when they're in the gas state and how that's related to temperature, pressure, volume, and things like that. And so I wanted to start off with a little demonstration that I've done many, many times. In fact, my own kids are sick of it. But it's a really, I think, amazing, very simple demonstration of something that we don't really think about that's around us all the time, which is the air and the pressure that the gases in the air are exerting on us all the time. We don't notice it most of the time. Maybe if when you go up in an airplane, you feel your ears pop going up and down, or if you dive into a body of water and you go down deep, you feel the pressure. But typically, on an average day, just walking around, or if you're like me and you've got bad hips, you feel the pressure when the weather changes. You can predict the rain, but generally we don't really take notice of it. So I wanted to show you that it is real and it happens with a very quick demonstration. But just to give you an overview of this week, all right, I'm going to do this demonstration, and then I'm going to switch to kind of a little explanation of what you're about to see using some of the stuff we're going to be talking about this week in class. So here we go. All right, so we're out here outside by the grill. I've got an empty soda can here. I've got just a little cup with some water in it, and then I've got this pan with some iced water. Okay, and then I have the grill going. I put the grate down a little bit lower because I want to get the can closer to the heat once it gets going. So what I'm going to do is I'm going to take the can, right, which is it's empty. There might be a couple of drops. But again, one thing to keep in mind is that even though it doesn't have any soda in it, it's actually not empty, which is something I'll talk more about during the explanation of what you're about to see. So what I'm going to do is I'm going to take a little bit of the water, just a tiny bit, and pour that in there. Okay, so you can hear there's a little bit of water in there. And then I'll put this whole thing onto the grill. Okay, and I'm going to let that sit. I should put it over here because this is a little bit warmer on this side. Alright, so I'm going to let that go for a minute. And I'm going to cut away for a second, just to let that heat up. But all I'm going to do, the only thing that's going to happen in the next minute or so, is that can of Coke is going to heat up. So I'm just waiting for that to happen. Okay, so I didn't cut away there, just because I want to show you that there's nothing special going on here, no tricks. I did speed it up because it takes a few seconds, and it's kind of boring to sit there and watch it happen. But what I want to show you really quickly, if you can see there's a little bit of something coming out of the top of the can. Okay, and what that is, right, what do we put in there? We put water in there. When you heat up water, what happens? It boils and it turns to steam. So what's going to happen next is I'm going to pick up that can in a second. Actually, what I'll probably do is slide it down again, all while the camera's rolling, because what I really want to do is get it closer to this cold water over here. And I'm going to focus the camera on the cold water, because what's about to happen happens really quickly. So I'm going to take the can off the heat, and I'm going to flip it over. So that's kind of key. I'm going to flip it over into the cold water. Ready? Okay. So hopefully you can see what happened. The can completely collapsed in on itself, or imploded is another word for that. Okay, so now I'm gonna cut away, and I'm gonna go to a slightly different setup so that I can explain what just happened. All right, so what's happening in the demonstration that you just saw? We start out with the can. Okay, so we're looking at like a cross-section of the can. And remember I said it doesn't have any liquid in it or any Coke in it, but it's not empty. Because what is in there, before I added the water, is air molecules, right? There's oxygen, nitrogen, argon, all sorts of stuff. Okay, so it's full of air is what it's full of instead of Coke. And then what I did is I added a little bit of water to the bottom and then added some heat. Okay? So the heat turns the water into steam. And then the steam starts to fill up the can. And that pushes the air out. Okay, so now we have the can, and now what it's full of is steam, which is just the gas form of water. Now that gas, that steam, is made up of molecules that are all bouncing around inside the can, okay, and they're bouncing against the sides of the can. That pressure, right, is what's exerted by the molecules trying to move outside the can. They bump into the walls, little tiny molecules, but there's lots and lots and lots of them. So they're exerting a pressure on the can. Right? That's why if you heat up a can of aerosol, like a hairspray or something, eventually it explodes because you're heating up the gas in there, and it exerts more and more pressure on the outside of the can until the can ruptures. But in this case, that's actually never going to happen because we have the opening in the top, right? So that there is some, you could see the steam coming out, okay? But what the purpose of having the water in there is that the steam actually kind of pushes all the air out. So the only thing, it's not 100% true, but most of what's in the can now is steam. So then what I do is I turn the can over and I put it into the container of cold water. And importantly, I flip it over, right? So now this opening up here is closed because it's under the water when I put it in the water. Now all that steam that's in there exerting pressure on the outside of the can turns back into liquid water because I cooled it off. And when you cool off steam, it condenses and forms liquid. So the gas that was in there was the steam. When that gas turns back into liquid, it takes up a lot less space and it exerts a lot less pressure. Now, it's not a perfect vacuum, which is not really a thing, but there's still some air molecules and there's still some water gas in here. It's not perfect, but I take away most of the gas molecules by turning it back into liquid water. Now that there's less steam molecules in there, there's less steam molecules bumping into the outside of the can from the inside. Okay, and that means that there's less pressure. Right? So instead of, let's say I drew 100 of these arrows, instead of 100 now there's only 2. So there's much less pressure on the inside of the can. So what? Well, what I haven't talked about yet is the fact that the outside of the can, of course, is surrounded by air, right? The air that we breathe, the air that's outside. Okay? That air is constantly pushing on the can. Now, when the can is open, the air is inside and the air is outside, right? And that's pushing from all directions with the same amount of force, the same amount of pressure. When I take the air out of the inside, mostly, okay, by filling it up with steam, okay, now the steam is what's pushing out from the inside of the can to counteract the air trying to push in. Then, when I turn that steam back into liquid, it's not that there's nothing pushing in from pushing out from the inside, but most of the pressure from inside the can is now gone. So all that's left is the pressure outside. Okay, and like I said in the video, we don't think about this very much, but the pressure of the air is about 14.6 pounds per square inch, PSI. Okay, that's not the unit we use in science, but it's something that we're kind of used to, and it'll hopefully make more sense in a minute. So pounds per square inch. That means for every square inch of surface, there's about 14.5 pounds of pressure. Well, the outside surface area of this 12-ounce can is roughly 67 square inches. 67 square inches times 14.6 psi is about 978 pounds. So that means that, again, it's not perfect because there's some error in here for air that's still in the can or steam that doesn't get turned back into liquid. But even if it's say a 20% difference, we're still talking about 700 or 800 pounds of force pressing on the can from the outside compared to very little pressing back from the inside. And that is what causes the can to collapse. Okay, it's just like I dropped a 900 pound weight on the can. Same idea. Okay, so again, we don't think about this very much. And if you think maybe this doesn't seem that impressive, I squished a soda can. We can all do that with our bare hands. But I'm going to show a clip in just a second because they did a giant-sized version of this on Mythbusters. And it hopefully will really drive home the power of just the air around us and the power of pressure and gases. So take a look at this short clip and see what you're going to see, and then this is what we're going to be talking about all week, is how gases behave, what happens when you change the temperature, the volume, the pressure, and how we can use a couple formulas to figure out exactly what those changes will be. All right, here we go.